So our objectives for today in our section 5.2 properties of exponents are being able to simplify expressions using properties for exponents and then using the definition of a negative exponent. And so in terms of just foreshadowing some formal notes that you guys are going to see, negative exponent, the main thing that you should really know is the fact that x to the negative 1 is the same as just 1 over the positive version of what we started with. 1 over x to the 1, right? X to the positive 1, which is the same as 1 over x. And you can apply this famous fact to any variable with any negative exponent. So if I were to say, okay, well, what about r to the negative 28? How do we put that in terms of a positive exponent? Does anyone want to help me out with that? It's 1 over the positive version of this, which is r to the positive 28. Whereas that first bullet point, simplifying using properties of exponents, we're going to learn the rules when you multiply numbers that contain the same base. You simply add the exponent. So x to the second times x to the third gives you x to the 2 plus 3, which is x to the fifth. When you divide numbers that have the same base, you simply subtract the exponent. So for example, x to the 10th divided by x to the third is the same as x to the 10th minus 3, which is just x to the 7th. Another rule that we'll hone in on is if you raise an exponent to a power, this is the same as multiplying the exponents. So x to the 7th raised to the 4th is the same as x to the 7 times 4, which is simply x to the 28th. And so these are the main rules that we will cover in today's section. I will go over them more formally in some later notes, and then we'll do a bunch more concrete examples as well. Okay, so the first one is really just understanding our exponent notation and knowing that the sort of big number on the bottom, and maybe I'll make this a little larger so you could see it, but this large number represents our base, and then our exponent is just what it's being raised to, that little number on the top. So when we look at these three examples below, from a numerical standpoint, if we have a fraction 1/2 raised to the 5th power, this just tells us that we're repeating this fraction 5 times. The exponent tells us how many times we're using this base as a factor. 1, 2, 3, 4, 5. And then we're straight back to multiplication. We multiply these 5 fractions by one another in order to simplify. So we have 2 times 2 times 2 times 2 times 2 gives us 32. And then obviously 1 times 1 times 1. If we multiplied 1 a million times, we would still get 1. Our second example is when we're dealing with exponents. And there's a huge difference between us having parentheses around our number versus us not, especially when we're dealing with negative values. And that's because if we're raising a negative in parentheses to an even number, then that tells us that we're going to have an even number of negative signs. And when we multiply an even number of negative signs, they all end up canceling out and becoming a positive. A negative times a negative is a positive, and a negative times a negative is also a positive. So we end up with a positive, and then 3 times 3 times 3 times 3 gives us 81. Whereas if we didn't have the parentheses, What we're doing is we're actually just solving the 3 to the 4th first, which still gives us 81, but then you want to tack in that negative sign at the end. So without the parentheses, it actually just stays negative. One last thing I want to mention is, let's say if we go back to problem B and we raise this to the 3rd power, what do you think is going to happen to our results here? The number's going to change. It's now going to be 27, but is it going to be positive or negative? Yeah, exactly, because now we have an odd number of negatives. Right. So our first rule of exponents, which was, if we went back to our objective, it's this guy right here. It's getting that imprinted into your mind, is known as our product property for exponents. Hence, if you multiply numbers that contain the same base, you're simply adding the exponents in order to simplify. So from a general standpoint, if we have a to the m power times a to the n, notice that they have the same base here, then we can just simply add the exponents. This is simplified to a to the m plus n. And then we have a nice numerical example below. 5 to the 4th times 5 to the 2nd. Well, what's 4 plus 2? 6. That gives us 5 to the 6th. And we're done. So now, knowing this rule, let's tackle these 3 examples together. The first one, add the exponents. What do we get? 5 plus 6 gives us 11. Right. Try to contribute. I know the people who are volunteering a lot more than the people who don't. Okay. 2 to the x times 2 to the 3x gives us? Good. 2 to the 4x. And then our last one, we have 2a to the 7th times 3a. Well, 3a is the same as 3a to the 1st. What do we do to the coefficients here? Do not add them. What operation are we utilizing? Multiplication. So what's 2 times 3? 6. And then we go to adding those exponents. A to the
8.
Yeah. Okay. Our next rule is our property for division. So that was, if we went back to the objective, that is this property here. When we divide exponents that have the same base, we subtract the exponents. So we have 2 concrete examples here. We have our x to the 5th divided by our x to the 2nd, and we have x to the 2nd divided by x to the 3rd. And so how do we write this in expanded form? Well, we have 5 x's in our numerator, 2 x's in our denominator, and then let's see what cancels out. An x divided by an x is 1, and an x divided by an x is 1. So how many x's are we left with? 3, also known as x to the 3rd. We can utilize the same process in that second example. X divided by x is 1, x divided by x is 1. So what are we left with? An x in the denominator. So we have a fractional result, in this case, 1 over x. And so this is the more formal way of writing out this rule. Quotient is just a fancy way of saying division. You know, some students can get tripped up over this word. And so again, if you're dividing numbers that have the same base, you're simply subtracting the exponents. Notice how we have two different examples here. I don't want you guys to get confused. This first one is just saying if m was greater than n. And the second one is saying if n was greater. If n was greater, then you're going to end up with a fractional result. But what I like to do is, for example, let's say we had like a to the 10 divided by a to the 21st. This is the same as a to the 10 minus 21. And then, ooh, you get a negative exponent, a to the negative 11. And then you can use that negative exponent fact. Well, this is the same as 1 over the positive version of it. That way you really don't have to memorize both of these rules. You just have to know the difference when you're dividing. Okay, so now knowing that, let's tackle these few examples together to practice our quotient, aka our division property. So first example, what's 9 minus 7? 2. So x to the 2 is our simplified answer. Second example, someone want to help us out with this one? 3 to the anyone? Sahi, do you want to help me out? Yeah, exactly. 10 minus 2, which gives us 8. Good. Class time is the time to really test your abilities, make mistakes. When you make mistakes in class, you're much less prone to making them on the assessments. The next example. What's 8 minus 12? Yeah, and now how do we make this a positive exponent? Yeah, so 1 over b to the 4th. Well done. Nice work, Caesar. And then the last example, 7 to the 3 minus 5. What's 3 minus 5? Negative 2, which is the same as 1 over 7 to the positive 2. Good. Which is the same as what's 7 to the second power? 49. Well done. Yes. Yeah. Sometimes they don't even specify it, but it's implied you want to. Whenever it says simplify fully or simplify the expression, you want to get rid of the negative exponents. Most of the time, I would say on assessments, the math department is very explicit and they're like, please make sure there are no negative exponents. But good question. All right. Our next rule, which is more just like a famous fact that I think you guys know already, but it's always good to refresh. But our zero exponent property, simply stating that anything to the 0 power is just 1. And we can maybe derive this rule really quickly off to the side here. Let's say we were looking at a to the 5th power divided by a to the 5th. And now numerically, let's let a be equal to 2. So 2 to the 5th divided by 2 to the 5th. Well, if the numerator and the denominator are exactly the same, this ends up just being what? 1, right? 2 to the 5th is really just 32, right? 2 times 2 times 2 times 2 times 2. And isn't 32 divided by 32? 32 goes into 32 one time. But utilizing our properties of exponents, our quotient property, we subtract the exponents. What's 5 minus 5? 0. Oh, that gives us a to the 0. But didn't we just prove that a to the 0 is 1? So that's our just simple derivation showing us that anything to the 0 power is 1. Okay. It's a nice, easy example after we did this derivation. What's 9 to the 0? 1. What about n to the 0 power? Yeah, exactly. Because anything to the 0th power is 1. This is our formal definition / slide for our properties of negative exponents, which we've been practicing a bit together at this point in the lesson. But essentially, whenever you see a negative exponent, it's the same as just 1 over the positive version. One over a to the negative n just ends up being a to the positive n. And how do you see that? Well, again, that a to the negative n is the same as 1 over the positive version. And then you can turn that numerator into a fraction 1 over 1, and then keep change flip. So we have 1 over 1 times a to the n over 1, which spits out our a to the n. But again, you don't have to memorize both of these. As long as you know one of them, then you're good to go. So now knowing that, let's practice these 4 examples. X to the negative 5 is the same as 1 over, is it? X to the 5th, good. I'm really tired today. 10 to the negative 3 is the same as 1 over 10 to the positive 3. And what's 10 to the 3rd? 1 with 3 zeros, also known as 1,000. All right, what about 1 over y to the negative 4? This is just y to the positive 4. And then what's the last one? Which is simplified to? Good. Thank you, Saeed. Again, might be a good idea to not be on your phones and to really pay attention. The person I'm directing it to is in the zone somewhere else. Okay. Now a fraction to a negative power property. This is just one step up from your knowledge of negative exponents. And so you can utilize your knowledge of 1 over the positive version of it, which is essentially 1 over and then utilizing keep, change, flip. Or if you ever see it, you just know that you're just flipping the numerator and denominator and then making the exponent positive, which could save you time, especially if you have like a real complex fraction that you're dealing with. But this is really just the shortened version of utilizing keep, change, flip. So now knowing that, let's see. Is your name Mia? You want to solve this problem for us? What do we have? Break it down step by step. is why you should be paying attention. Does anyone want to help her out? Beautiful. Thank you, Nor. And then we can actually simplify this a bit more because we have numerical values. So we can bring that 2 to each term in our numerator and denominator. So we're looking at 7 squared over 5 squared. And what's 7 squared? And what's 5 squared? Well done. All right. You want to redeem yourself and go for the purple? So what does the negative exponent tell us? What do we do to the numerator and the denominator? We flip them. So now we're looking at, we can keep that negative in the numerator, so it really doesn't matter if it's on the bottom or top, but we're gonna have y in our numerator now and x in the denominator. And now because they're flipped, that -3 becomes a +3. All right, now what's our next step? Yeah, we want to distribute that 3 to each term. So we're looking at negative y to the third over x to the third. And then we're done. We can't simplify it any further after this. So we're going to step up our game a little bit now that we have a better understanding of negative exponents. And we're going to combine some properties together. We're going to combine our knowledge of negative exponents with our knowledge of product property. So z to the -5 times z to the -3. Anytime we're combining properties, my recommendation is to stick to one property and then utilize the other. Because there are some cases where if you stick to one, you don't even have to end up using the other. So for example, if I went to product property first, I'm adding the exponents, which ends up giving me z to the -8. And then I can use my knowledge of negative exponents to say that my answer is 1 over z to the 8. I think that's personally easier than if I put these both into fractions first. I mean, in this case, the other way is pretty similar in the number of steps. But the cool thing about doing product property first here is what if we were dealing with division, for instance, and we had z to the -5 divided by z to the -10. Well, this is the same as z to the -5 minus -10. Two negatives next to each other give us a positive. So we're looking at z to the -5 plus 10, which is z to the +5. So we never really needed to utilize our negative exponents property. All right, let's look at this second example here. I'm just going to underline some common variables. So with our purple, we have m to the 4 plus -5. And with our n, we have n to the -3 plus -2. So this simplifies to m to the -1 times n to the -5. And now let's put it in terms of positive exponents, 1 over m to the 1, which is just 1 over m, times 1 over n to the +5. multiply the fractions, and we get our final result to be 1 over m n to the fifth. And we're done. Any questions on that last example? How are you guys feeling with this material so far? One being like, I am so lost. I have no idea what's going on. And 5 being like, this is quite straightforward. I can teach it to someone else. Right, cool. Good, good, good. Awesome. I would say if you are below a 3, so if you held up a 2 or a 1, see me after class. And if you're at a 3, I would say try to practice a few more examples together on your own later today. Okay. Our power property for exponents, which if we go back to our objective, that was this rule that I stated way back in the beginning. If you're raising a term to an exponent, you're simply multiplying those exponents together. So the slide that we're currently on is just formalizing those notes. So more generally, if we have a to the m raised to the nth power, we are once again just multiplying those exponents. So that just gives us a to the m times n. And so now knowing this rule, let's apply it to these few examples. Y to the 5th raised to the 9th gives us, what's 5 times 9? Good. So y to the 45th. What about 4 to the 4th raised to the 7th? Multiply the exponents, and what do we get? 4 to the, not 24, 28. Yes, nice. And I would simplify that, but that is a very, very large number, so we can just keep it as 4 to the 28th. And then this last one, let's do it separately first. Y to the 3rd raised to the 6th is just y to the 18th, good. And then y to the 5th raised to the 4th is just y to the 20th. And now we're multiplying two numbers that have the same base. So what do we do to the exponents here? We add them. So what's 18 plus 20? 38. So our final answer is y to the 38. Nice job, William. Right. And so this next rule, we have product to a power property for exponents. So this is just showing that if you have two terms here, whether they're numbers, whether they're other variables, what's happening is you need to distribute that exponent, if it's in parentheses, to each of those variables. You cannot forget to do that. The most common mistake that I usually see is if we have, and I've seen this made on both quizzes as well as assessments, but let's say we had like 2 to the x in parentheses raised to the 3rd power. A lot of students are like, oh, let's just distribute the 3 to the variable. This is just 2x to the 3rd. Is that correct? No, because you have to distribute the 3 to both the 2 and the x. This is actually equal to 2 to the 3rd times x to the 3rd. And we know 2 to the 3rd is just 8. So 8x to the 3rd. So now knowing that, let's practice these 4 examples together. Again, bring that exponent to each term. So we get -3 raised to the third, m raised to the third, and n raised to the third. And -3 raised to the third is what? What does that end up being? -27, right? 3 times 3 is 9 times 3 is 27. So our final simplified result is -27 m to the third, n to the third. Anything to the 0 power is 1. Saves you some time. All right. First, let's distribute the negative, and then we'll deal with the rule of negative exponents. So we get 6 to the -2, and then k to the -6. And so now we can deal with the negative exponent. They're both negative, so we can just put it as 1 over the positive versions of both. 6 to the second, k to the 6th. And what is 6 to the second? 6 times 6 gives you 36. And then k to the 6th stays the same. And we're done. Last example, we have 5 to the second. X to the -3 times 2 is -6. 5 to the second is 25. 25 as a fraction is just 25 over 1. And why am I doing that? Well, because that second guy, that x to the -6, is going to be a fraction as well. It's going to be 1 over the positive version, so x to the +6. And now when we multiply this straight across, we end up with our simplified answer as 25 over x to the +6. And we're done. Any questions on any of these examples? No. Okay. And I believe this is one of our last rules, our fraction to a power property for exponents. I feel like I'm running out of highlighter colors. But in this example, it's very similar. It's just we're dealing with the fraction this time. So if we have a fraction raised to an exponent, you have to really make sure you distribute that exponent to both the numerator as well as the denominator. And these first two examples are pretty straightforward, but these second two, you're distributing that 3 again to each of the terms in the numerator and then to each of the terms in the denominator. So for our first example, we just simply have b to the 4th divided by 3 to the 4th. And 3 to the 4th is just 81, so we can simplify this to b to the 4th over 81. Second example, oh, it's a negative exponent and it's a fraction. So what can we do first? Yeah, flip it to make it a positive exponent and then bring in that exponent to each of the terms. And then we're done. Our third example, you want to make sure you're distributing that exponent 3 to each term in our numerator. 2 times 3 gives you 6. And then each term in our denominator, we just have 1, so we have z to the third. And then we can simplify that 2 to the third, that just gives us 8. So our final result is 8x to the third, y to the 6th, all over z to the third. Same process with this last example, distribute that 2 to each term. in your numerator. 4 to the positive 2, p to the negative 6, and then each term in the denominator as well. Q, 2 times 2 gives you 4. And we have a p to the negative 6 in our numerator. How do we make that positive? We just bring it down to the denominator. So we end up with p to the positive 6 in our denominator with our q to the 4th. And then our 4 to the 2nd is just 16. A few slides left. This slide is just a summary of all of the exponent properties that we covered in class today. So if you've been handwriting notes throughout the class, I recommend you putting this into your notes. And if not, then at least try and print this up later today and glue it either onto your wall or someplace that you can see it on a daily basis to help solidify these properties. This will pop up in pre-calculus, calculus, very, very useful in your future math classes as well. Right, so let's get into a few more complex problems. Create columns for these three. So we want to take it step by step. The first sort of term is being raised to the 4th power, so we need to distribute that 4 to each of our terms. That x is going to be now with what exponent? X, not 6, because you're raising, it's x to the 2nd raised to the 4th, which means we multiply these exponents. So what's 2 times 4? Yeah. And then y to the 4. And now let's look at the second one. We have 2 to the 3rd, x to the 3rd, and y to the, good. Now we can simplify. 3 to the 4 is 81. Our x to the 8 and x to the 3rd becomes what? X to the, what's 8 plus 3? 11. Y to the 4th and y to the 6th becomes y to the 4 plus 6 gives you 10. And then we have that 2 to the 3rd, which is 8. So our last step here is just multiplying 8 and 81, which is what? We know 10 times 81 is 810. And 810 minus 162 gives us what? Well, that's 710 minus 62. And then 700 minus 52. So 650 minus 2, 648, right? And then x to the 11th, y to the 10th. So that's our final answer. Look at our second example. X to the 3rd raised to the 4th gives us what? X to the 12, good. And then we have x to the negative 2 raised to the 5th gives us x to the, good. And then we have x to the 6th raised to the 5th gives us x to the, yep. Let's simplify the numerator first. We have all the same variables. What's 12 plus negative 10? Right, it's the same as 12 minus 10, which is 2. All over x to the 30th. And now we subtract the exponents. What's 2 minus 30? Let's put it in terms of a positive exponent. So we get 1 over x to the, and we're done. Our last example, we have 2 separate fractions. So don't forget to distribute that 2 to each term in the numerator as well as the denominator. We're looking at 2 to the second power, x to the second, y to the fourth, all over x to the what? 3 times 2 gives you 6, and then y to the negative 4. We'll keep that as is right now. And now this negative exponent, what does that just tell us? It flips your numerator and denominator. So that second fraction is just x to the third, y to the negative 1 in our numerator now, and that denominator is 12x y to the third. And now let's see if we can combine some terms. So in our numerator, 2 to the second is just 4. We have an x to the second, and we have a y to the third. Add the exponents, and we get x to the fifth. Then we have a y to the fourth and a y to the negative 1. Add the exponents, and now we're at y to the positive 3. All over. In our denominator, we have that 12. We'll put out in front. And then we have x to the sixth times x. 6 plus 1 gives us x to the 7. And then we have y to the fourth and y to the 3. Sorry, y to the negative 4. So negative 4 plus 3 gives you negative 1. We can do some more simplification from the division perspective. We have 4/12 is the same as 1/3. X to the fifth divided by x to the seventh. Well, 5 minus 7 is x to the negative 2. But x to the negative 2 would stay in the numerator. If we wanted to make it a positive exponent, we just keep that 2 in the denominator. So x to the 2 in our denominator. And then we have y to the third minus, or divided by y to the negative 1, which is the same as y to the 3 minus negative 1. 2 negatives next to each other give you a positive, so this is just y to the positive 4, so we can keep that in our numerator. So our final result is just y to the fourth over 3x squared. Done. Any questions on that last problem? Sort of combining all of our rules and properties that we've covered. These are very common problems that you'll see on assessments or quizzes. All right. So that was the end of our section 5.2 today. Let me stop recording this.